Hello everyone, welcome to lecture 12 of this course. In the previous lecture, we studied types and type systems, the background and the Haskell type system, some features. Today we are going to discuss type lambda terms and type language. Type lambda terms. There is no type in pure lambda calculus, so it is also referred to as untyped lambda calculus. Now we associate types with arguments and result. Lambda calculus with types is called typed lambda calculus. So, the notation that now we are going to present it formally, earlier we used it. So, notation, this is a notation m colon a, it has to be read as a term m has type A, or we can interpret it as a type A can be assigned to the term m. So, now earlier, so the point of shift when we move from untyped to lambda, earlier we are working with only one thing, that is a lambda term. Now we have another thing called types, informal idea we have got. Now we associate these two things and we say that m has type A. These two are different things. M is coming from the grammar of lambda calculus. A is a type that we are going to discuss. So, we are putting them together and we are saying that m has type A, or we say that type A can be assigned to that lambda term m. So, we consider several functions, all of these we have studied, and now we are going to write the typed version of each of the functions. So, the first one is the identity function lambda x dot x. Now, say we are associating, so x is the parameter of the function. So, we have to first associate, that is what we said, the simple object. So, simple object x is a variable, here x is a parameter, and we start with giving an assignment that x has type A, let x has type A. That means the type of this parameter is A. If that be the case, so we write lambda x colon, this notation now says for the parameter x, we are write within this lambda x, now x colon A means x has type A, then this body as it is, the body remains as it is. In the typed version, the body remains as it is, the parameters will be given some types. So, this is called the typed version of the identity function. Now, we are interested in what will be the type of this function. Now, function is a mapping from one set to the other. So, here it takes an input A and returns an output as A. So, it is a mapping from A to A. So, arrow means function type. Whenever we are having lambda x, that means it is an abstraction. It is a function type, and function type we are going to have this arrow. Arrow means function type. Now, suppose A we say it is int, so we will write int arrow int. So, we give a rule, say for remembrance purpose, one parameter in a lambda term means one arrow. So, here there is one parameter, so that means when you are writing the type of this function, we will have one arrow. Let us see whether this rule is true for more parameters. Now, consider the first function. Now, first function is defined as lambda x dot lambda y dot x. There are two parameters x and y, and returns the first parameter. So, the type version will be x colon, we just write x is A and y is B, and this body is like this. So, it will be first, then type will be in a similar way, the x is A and y is B and B. So, this says there are two arguments A and B. So, we write this way because x is first, so we write A, y is second, so we write the second, and then we write this. So, it is A arrow B arrow A. Now, this arrow, when we have more than one arrow, it is right associative. That means we can also say that A arrow B arrow A, but then this is not needed here. When this parenthesis is absolutely necessary, then only we are going to keep it, otherwise we will not keep it. So, however, arrow means it is right associate, it associates from the right. That means simply we have to put that we know that lambda x, this is lambda x dot lambda y dot x. This part is again a function. So, let this lambda x dot m. Now, this part will be type of A, arrow, type of m. What is type of m? This will be something. This is we will be B arrow A. This is how we have got this one. This is by currying. By currying we have got this. So, now again our rule then will be, we are going to have our rule will say that now if it is two parameter, now we have two parameters in a lambda term means two arrows. So the rule is applicable here as well. So A arrow B arrow is to be read as a function that takes as input an argument of type A and returns another function that takes an argument of type B and that returns output of type A. This is called currying. This is the currying idea. This is equivalent to saying that a function takes two arguments of types A and B and returns a type of A. That means this parenthesis may be removed as well. So we get this. Now consider the function second. So it is similar to, structure is similar to first, only thing is that now you have the body is changed. So the structure will be same, instead of A it will be B. So again it will be two parameters are there, two arrows. Now we see the apply function lambda f dot lambda x dot fx. Now x has type A. What would be the type of f? The type of f's argument is A, then return type is B, so f should be A arrow B. So then the type of apply will be, it is a first argument is a function, so it is A arrow B. Second argument is a variable, it is A, and return type is B, so we are getting B here. So this is an example of a higher order function, because input is a function. One is a function, another is a variable. We can see that the types of f and x must be different, because x is a variable, it is a simple object. Now f is a complex object, so it is an arrow type object. Thus we have the above rules. Now here also we have two parameters. So we have lambda f, lambda x. So there are two parameters f and x. But we said if there are two parameters there will be two arrows, but now we have three arrows. So the rule fails here. So then we need to understand what is meant by these two parameters means two arrows. So we will see to it slowly. Now why is this parenthesis needed here? Here why have we, earlier we said this part we remove the parenthesis, now here we have to keep the parenthesis. So suppose we omit the parenthesis, then we get this. This has to be read as, there are three arguments 1, 2, 3 and we are getting the result. That means first argument is a function of three arguments. First argument is of type A, second is of type B, third is of type A and returns this as B, which is not what was intended. So thus the meaning is changed. This meaning says this itself is a function, this is one thing function, this is a variable and this is. So we cannot remove the parenthesis here. Now consider the twice function. That means the apply function, now we are applying it one more time, fx, f of x. Now we want to find the type of this function twice. So x is as before, x is a variable, so we say x has type A. So then fx, x takes input A, output should be B. So fx has type B. That means f has type A arrow B. If that be the case, then this f input will be B and it will be B arrow C. But in the same definition, the argument types of that function cannot be different. Once it is taking input A, another it is taking input B, that is not possible in the same definition. That means B must be A. So then what we get is twice will be, this function type is A arrow A, input is x A, so we got A. Now the composition part, it will be, there are two functions and one variable x, so we are doing first f of x, then we are doing g, so it is g of f of x. So it is f is A arrow B, g is return type is B, B's input is B, g's input is B, so B arrow C. So we got A arrow B, B arrow C, A and C. Now again you see there are three parameters, there are 1, 2, 3, 4, 5, that rule fails. So we have to study this carefully. Now let us consider the Church numerals. So Church numeral, now you see this 1 representation, Church 1 in Church numeral 1 represented is lambda f, lambda y f. This is the apply function. And 2, this is the twice function. Now if we write 3, then 3 will be represented this way. So what will be the type of Church numeral? So can we generalize from twice or apply to this one? From apply it was different. It was A arrow B, A arrow B, arrow A, arrow B. Now twice was A arrow A, arrow A, arrow A. Now what will be then if I do it 3 times? Now what will be the type of 3? Will it be same as this or different? Let us see. So here it is taking A, F will be A arrow A, we know. So here this part then will be f of fi, this one will give us A. So, f will again take A and give us A. So, that means the type remains does not change here. So, we will call it like CHN. So, the charge numeral type will be this, it is the same as twice. Now, consider the successor function. So, successor function takes as input a charge numeral and it f and y, and it does f of n of fy. So, the type will be charge numeral, arrow f is arrow A, y is A, and output is a charge numeral, because return type again is a charge numeral. So, it will be like this. Similarly, add will be charge numeral takes two charge numeral, then f is arrow A. Now, you see that there are 1, 2, 3, 4 parameters. Here there was 3 parameters, but we have got more than 3 and more than 4 here. So, now see the rule. The rule says if there are n parameters, there will be n arrows. This n arrows means this red colored arrows is what we meant. Red colored arrow means the primary arrows, and these ones are internal. That means this is within that parameter. This parameter is a function, so within that this is there. It is a parameter. Outside is the type. So, that means n is of type charge numeral, f is of type something, that will not consider here. Y is say this. So, there are 3. So, there are 3 red arrows and output type is 1. So, this is the thing. So, we have to identify these red arrows, and that number of red arrows will be the same as number of parameters. So, if you are given n parameters, there will be these n red arrows 1 to n, and then we structure and see individually whether it has itself a structure or not. If it is a variable, it will be just A or B, whatever. Otherwise, it is a function type, then this itself will be an arrow. But the outer structure of red arrows we indicated, that will be only n. So, this is the idea of writing the types quite easily. So, given an arbitrary lambda term, we can write the type very easily. We know the outer structure, and then we just fit in the type of the individual parameters, and then we are done. Okay, now we discuss type. A type is a set of values. The basic type is defined as, a type is basic if its values are atomic. That is, if the values are treated as whole elements with no internal structure. Examples of basic types would be, say type bool. The basic values are true and false. For the type natural, the basic values are 0, 1, 2, etc. Thus, these types bool and nat are basic types since the values have no internal structure. This is the simplest thing that we can get. Using these simple structures, we can construct a complicated structure, that is called a composite structure. The composite type is, it is a structure like sigma arrow tau, where sigma and tau are types. So, that means if sigma is int, sigma is nat say, and tau is also nat. So, we have nat arrow nat. If both are bool, it will be bool arrow bool. So, now this is the composite type. So, we have two kinds of types. One is a basic type, that is the simplest thing that we can have. They have no internal structure, their values have no internal structure. Another composite type built from the basic types. So, for example, all the functions like identity, first, second, apply that we have seen are all examples of composite types. So, how to differentiate between two types? Composite types will always have arrow, that means they are functions, and basic types will not have any arrows, they will be A, we write A, we write nat, we write int, and so on. Now, we give an informal interpretation of types. Each type expression is interpreted as a set, the set of values of that type. So, when we say the type int, it denotes the set of all integers or the set of all natural numbers if we say the type is nat. That means intuitively, when we write sigma arrow tau, we are saying it is the type of all functions from sigma to tau. So, if int is the set of all integers, then int arrow int denotes the set of all functions with domain int and range int. Now, let us try to see the full set theoretic interpretation of types. A type constant b, we may denote it by any set like A superscript b. So, we start with a type constant b and we associate it with some set A b. Now, the function type sigma arrow tau denotes the set this A sigma arrow tau, that is a set of all functions from A sigma to A tau. This is what is called the full set theoretic interpretation of types. There are other interpretations of types. For this, please refer to John Mitchell's book. There are other types of interpretations also given. So, for our discussion, for our course, we will consider only this set theoretic interpretation. We have to keep in mind this set theoretic interpretation of types. Now, we discuss type language. Recall the notation that m colon tau, this means lambda term m has type tau. This term m is coming from the grammar of pure lambda calculus. So, we can have lambda x dot x, lambda x dot lambda y dot x and so on. This will be the m. Now, we are assigning a type tau to m. So, say for example, we write lambda x dot x, this is our m. This whole the m has a type, we said, we discussed that it will be of type a arrow a. So, when x has type a. Now, this a arrow a, I mean this also is coming from some language, just as we have obtained this m from the grammar, this also will come from some language, some grammar. So, there are different types of languages possible. So, we will consider one and show others as well. So, that means this will be a sentence of some language. So, what are those languages that we are trying to understand? So, we start with a very simple language that is defined in this way, that first let us assume that we have a set of basic types that we denote by basic. So, an element of this basic type is a type, an element of this type is a basic type. So, we say k and we say if sigma and tau are types, so is sigma arrow tau. So, this is the grammar of this language. So, there is a, so earlier we discussed there are two types we can broadly classify, one is a basic type and is a composite type. So, this is the basic type and this is the composite type. So, suppose our basic set is nat and bool. So, the types that we are going to obtain will be nat we can get, it is a basic type, bool we can get, nat arrow nat we will get by this composite type. Then we can get nat, so tau I can replace by nat or nat, and then sigma will be nat. So, nat arrow nat and so on. So, we can get a whole lot of these types obtained from using these two rules here, basic type and composite type. This will be our simple language. Now, we introduce what is called a type variable. A type variable is a placeholder for an unspecified type. Just like if I say int x, that means x is a variable of type integer, that means x takes on a value of integer of anything. It can be 0, 1, minus 1, minus and so on, whatever the integer set is. Now, consider the Haskell definition of the identity function. So, it says id is a arrow a, so id x is x. So, it works for integer, strings, lists or any other types. So, if we say id 42, so here a is of type int. Here we say it is a hello, so that means a is of type string, and here id is this list 1, 2, 3, it is of list of integers. So, a will be the list of int. So, a is written this way, a is a list of integers. So, a is a called a type variable. So, there this definition then says a is a type variable here, that means it works for any type, it works for int, it works for string, it works for this. This is a placeholder for an unspecified type. This is the meaning of a type variable. Now, we define another language where we assume that we have a supply of type variables. So, we have infinitely many such type A, B, C and so on. So, a type variable is now a type, and if sigma and tau are types, then so will be the sigma. This is again the structure is same as the L1, but now instead of basic we have a is a type variable. So, let us see different examples. So, when we say lambda x colon nat dot x, it means that the type of the function is nat arrow nat, since x has type nat. So, here the function has only one type, this function has just one type. When we write x colon a, where a is a type variable, now the type is a arrow a, since x has type a. Now, a can be instantiated to anything as we have seen. So, a now this function has infinitely many types. Now, we can instantiate with nat. So, it will be this x colon nat. When When A is replaced with nat, we get this one. So, that means earlier one language we had this 1, when we supplied that x colon nat, we used to get these types of terms we are going to get. In L1, from the language L1, we are going to have this x colon nat dot x, this type of lambda and type annotated terms we are going to get. Now, we are going to get this sort of terms, where the difference here is that x A is a type variable, but here x was explicitly given a type called nat. So, we are in this, when we explicitly assign, it will have one type whatever is specified. Here it will have infinitely many types in the language L2. The types obtained from L2 are called weak polymorphic types. Weak because it has no universal quantification, that is for all types. For all types we do not have. So, that is why it is called weak polymorphic types. So, the typed identity function will look like this way, lambda x colon A dot x, and the type is A arrow A, where A is a type variable. Thus, we have seen that identity function has infinite number of types. We are going to adopt the terminology from Hindley's book, so that is weak polymorphic types. This L2 we are going to refer as weak polymorphic types, and this will be our working language. All throughout subsequent lectures we are going to use L2. When A is instantiated to int, the identity function has type int arrow int, or if it instantiated to nat, it will be nat arrow nat. This is an example of a monotype. Monotype is a type without type variable. It is a concrete type that does not use polymorphism. So, that means L1 language we are going to get monotypes. Now, we move on to the strong polymorphic type. Now, the addition here is, it is L2, now we have added this part. So, for all quantification was not there in L2, now we have for all quantification. So, it is for all A is a type variable. So, as before, this part is same as L2, this is L2. Now, this part is added here, and we are saying for all A dot sigma. This is called universally quantified types. So, for example, so when we have this term lambda x A dot x, so this term x is a bound variable, but A is because it is a type variable. If we look in terms of variables, this is not a closed term. If we look in terms of variable, this is not a closed term because A occurs free. A occurs free. So, we will try to make it a closed term. So, the idea would be then we will say lambda A will be the parameter, and we write as before. So, this is called the parametric identity function. Now, it is a closed lambda term. It is in terms of, it is a closed term. Now, there are no free variables. So, this is the body of this term. Now, when we instantiate it with say A, we will get back this one. So, we will get lambda x dot x colon A dot x. Now, the idea is, if this body M, if this part is say M, if this part has this type sigma, then when we introduce this parameterization of this type variable, we get for all A dot sigma. This has to be read as for all A, for all types A, M has type sigma. So, we write for all types A, M has type sigma. This is written in this way, for all A dot sigma A arrow A. A arrow A part is the sigma here, and A arrow A you can get it here. So, this is called polymorphic abstraction. This technique of writing this, when we are parameterizing this variable, is called polymorphic abstraction, because now we are applying this as a parameter. So, for this please refer to this classic paper of Luca Cardelli. So, there it is discussed in detail. In our course we are not going to work with L3, we are only going to study L2. It is for the sake of understanding, and later on we will try to correlate how to get the results for L3 from that of L3. To what extent we can get, that we will study later, but we should also have knowledge that okay, what is the idea about weak polymorphic types and what is the strong polymorphic types. So, thus we have studied different type systems based on the language of types. So, that m has type tau, we know tau can be from L1, tau can be from L2, tau can be from L3. So, let us compare these 3 languages L1, L2, L3. As we can see, L3 is an extension of L2. It has for all types. So, it is more expressive than the other 2. L1 is the least expressive among these 3, and L2 is intermediate in L2 between L1 and L3. It is more expressive than L2, but less expressive than L3. Now, we are going to study a type system for L2. So, we will develop the theoretical aspects, theoretical framework for the language L2. So, there are 2 important problems associated independent of the language, that is called, first problem is called the type assignment problem. So, given an untyped lambda term, determine if m is typeable, or we can also say determine if a type can be assigned to m. So, that means we are given a lambda term, problem 1, we say we are given a lambda term m, whether we can associate a type tau to m or not. This is called the type assignment problem. So, for example, if I have a lambda term like lambda x dot x, I can associate that this type will be A arrow A. From the knowledge that we have obtained, it will be A arrow A. But if I give an arbitrary lambda term, say for example, lambda x dot xx, this is SA, what will be the type of this? So, recall that when we studied typed lambda, that we are doing type annotation of lambda terms, we said we have restricted it. That means not every lambda term will not be having types. This will lead us to SA we will know it is going to give us beta reduction SA, non-terminating, that is big omega. So, these things are not meaningful. So, they will not be typeable. Later we are going to prove that these type of terms are not typeable. So, that means only certain kind of terms will be typeable. So, the idea is whether we can come up, this is a decidable. So, this problem is decidable or not, we have to see. That means if it is decidable, that means there will be an algorithm that will take as input a lambda term and it will find out whether it is typeable or not. First it will find out whether typeable or not. If it is not typeable, it will correctly say that look, this is not type. This, for example, the algorithm should report it is not typeable. And if it is typeable, it will give a general type, most general type, that again it is a terminology we are going to discuss later, a general type. This is a general type of the identity function. This is what will be if the problem is decidable for some language. If it is undecidable, that means there will be no algorithm for this language. So, we are considering L2 and this problem is known to be decidable. So, this is the idea about expressivity. When we make the language very expressive, it may not always be decidable. So, what extent the decidability aspect remains is interesting. So, L2 is a language, that means that we have studied, that has this decidability. That means we are going to have an algorithm and we are going to discuss that algorithm here. That means input will be m, we are going to, algorithm will tell either m is not typeable or it will say look, this is typeable and the most general type is tau. So, this is called the type assignment problem. Now, the reverse problem is the type inhabitation problem. Now, we say that okay, tau is given, tau is a type from a given language, say L2. Now, we are saying okay, whether we have an m or not, whether we can have there is an inhabitant, that means there is some lambda term that has type this. So, now we are given this part. Now, say we are given A, this is our type. Now, we say okay, what will, is there any lambda term that has type m, that has type tau? Now, again for L2 there is an algorithm. So, we know this term is lambda x dot x, this has type A. But again we go for, and this is again a fundamental result that we will discuss. This coming from this tau to this one is a fundamental result, and that is the heart of the discussion of type lambda calculus. So, when we make the language very expressive, these problems tend to become undecidable. For L2, these problems are decidable, and we are going to show the algorithms or the method for obtaining the both from m to tau and tau to m. This is what we are going to study next. So, let us summarize. So, we have discussed the types of some lambda terms and we have studied different type languages and the different problems that are important and to be studied. So, with this we stop and we request you to please see these articles of this is the book by Hindley and this is a Cardell's paper and John Mitchell's book. Thank you for your kind attention.